So this will be generated, needs a little bit of time because it's a big amount of data, and you will get then in that email information of the seminar also the information where you can find this record. This will be available then for approximately 4 weeks then, so that you can hear that again. So now I think we are ready to enter now. When you are in such a situation, I think that makes it quite clear what the goal is in appearance evaluation, appearance measurement, and also appearance optimization. We want to have a uniform look around the painted car parts. So this is one of the highest goals. Of course, we want to have a very nice appearance, no question, but very important is that we don't see any disturbing differences between parts which are quite close together, the adjacent parts here. Let me give you an overview about our topics for today. I will start with a view into the rear mirror and show a little bit the milestones in the history of appearance. I will continue then to give you a short review of the wavescan measurement technology, the principle, and continuing then with customer-specific scales to evaluate appearance in a way like the users are used to. And last not least, I will come to our new generation, which is surely a topic which many of you are expecting for, our new wavescan family, the wavescan 3. And finally, I will give you also a small outlook on that, what can be expected for the near future now from our company. But let's take a look back. Evaluation of appearance being visually or instrumental goes back into the 1930s, 1940s of the last century. And there it is, Richard Hunter, who was a pioneer in measurement of appearance criterions, who defined that gloss is more than just a simple specular gloss measurement. Gloss is a multidimensional aspect and needs to be described with more than just one number. And he defined then 5 aspects of gloss, some for the high gloss range, some for the medium gloss or low gloss range. And on the first place, of course, the specular gloss of high to medium gloss surfaces, then focusing more on very high gloss surfaces. He also introduced the haze and milkiness, besides also distinctness of reflected image, which is more or less the sharpness of an outline of an object. And looking on the low gloss surfaces, he found an effect which is called sheen. So when you look very flat on a surface, you get that it starts to get an amount of glossiness again. And for low gloss textiles, he found what many people know under luster or contrast gloss. Let me show you shortly the principle of the gloss meter, the standard classical reflectometer. We have here an illumination on one side under a certain defined angle, and we have on the other but opposite side the same angle, sensorics, which measures the reflected light. And there it was, the first gloss meter, 1934, which had a 45 illumination angle, 45 degree. So that's the easiest way to do, just a half of the 90 degree. But the users found then in some cases that the correlation is not so good for a wide range from matte to high gloss. So further development work took place. And in 1939, a so-called 60 degree geometry was introduced, which had a very good overall correlation with the visual rankings. But even at that time, people recognized that there are borders on the very high gloss and very low gloss range. And so in 1947, an additional geometry was an 85-degree optimized for measurement of low gloss finishes, very matte surfaces. And a few years later, in 1951, additionally, a 20-degree reflectometer was defined, which looked under more close to the perpendicular. And you see here, it is not only a lamp and a detector. You need, of course, a defined geometry, an optics, some lenses, filters, and so on. And finally, the gloss meter today is a very specific optoelectronic measuring tool. Besides, now, even with a 20-degree gloss meter, there was a border to define very fine scattered light. And there I want to point out here the haze. This is a kind of milkiness. When you look on such a sample, you get a good reflected image, but there is a milkiness overlaid. And that was caused mainly, you know, that from painting maybe, when pigments are dispersed in the resins, you need a good dispersion process. Otherwise, you can have some flocculation or agglomeration, so larger particles than the optimum, and these particles can target on the surface and create then this very fine scattered light. Compared to the left sample, which gives a perfect image, you have then this reduced contrast of a reflected object. Besides that, and as I said before, this is an effect which cannot really good differentiated by a classical gloss meter. Another effect is what's called distinctness of image. This is an effect not only on paints, that was very common also on chromated parts like bumpers, door handles, and so on, which were more spread in the market in the 1960s, 70s. And to see here in this example that the pattern of the background here is not so good reflected on the left part than on the right part. So this is not so sharp here on the left side. This is also an effect which is not really to be measured with a specular gloss meter. So that were all effects which have led to a development at Hunter of the so-called Dorigon distinctness of reflected image gonio-reflectometer. Gonio because now not only under the reflected 30-degree angle of the illumination, we have several detectors here under different angles, and each of these sensors are for different reasons. We have two sensors for the haze and then additionally for the DOI. As you can see here, that was a benchtop instrument which had a measuring head and a calculation unit. Critical of this measurement principle was the influence of the curvature of samples. So if you have a curved sample, that will influence your measurement results. So you couldn't compare flat to curved parts. Another shortcoming was the influence of macroscopic structures. Orange peel had an influence on the DOI values. So that can be used only on non-flat parts. The Dorigon production was discontinued in 1987. And it was in 1990 where Gardner introduced a laboratory instrument to measure the specular gloss in the classical geometries like 20, 60, and 85 degree. But also it was implemented sensorics with two additional sensors to evaluate the haze. And that was very close to the 20 degree, that means to the high gloss reflectometer sensorics. I will introduce here now a visual tool. There were several boxes, apparatuses which helped to make a more standardized observing condition on the illumination side, but also on the observing side. And this here was very widely used to evaluate DOI as well. This is a so-called glow box. This kind of principle is always a kind of box where you have some illuminating a pattern, and the pattern is then reflected over the sampled surface, and the observer can look then on the surface under defined distance then. And the patterns could be numbers, could be letters, but very often you find these so-called Landau rings, which are circles with a gap included, and the observer then looked on the smallest size, but also on the gap orientation to be recognized here in the reflected image. And then you see here kind of scaling from 10 to 100. And if you can recognize really the very small circles and the gap orientation, then you have a very high quality. If you can only recognize figure number 10 and 20, then it's quite poor. Coming now more to the real effect of orange peel, the macroscopic structures, then I want to show you here a definition of the ASTM E284. This is a standard describing standard terminology of appearance, gloss, haze, but also orange peel. And there you can find a definition which is called the appearance of irregularity of a surface resembling the skin of an orange. Yeah, I took here a direct comparison between an orange and a typical car paint. You see there is no longer really this strong structure like we found on orange, but orange peel is an expression which is widely used in the market, and everybody knows when you talk about orange peel what is now the issue. So, and here I will come to another kind of visual tool. These are kind of samples or reference panels which are used in many plans also. Mostly known as are here these ACT rating panels, came mainly from the US side. These are 10 panels which are ranked from a very strong structure to very good quality to a very smooth surface. The ranking here goes from 1 to 10, 1 saying for a high amount of structure and 10 for very smooth. And you can see for vertical part, it is expected to be better than a value of 5, and for horizontal parts, even better than 7. I come a little bit later to these correlation formulas, but I want to point out here, just for understanding, we have also correlation scales in the wave scale instrument, which calculates from the raw data scales, like in this case here, the rating of these ACT panels. And what we found there, that the formula is based mainly on the influence of long waviness. There is a small influence of short waviness, but the main influence is from long waviness. What I also want to point out is that, of course, this way of quality control is strongly dependent on illumination and viewing conditions. Often they are not really defined, can change, and that means, of course, that the final judgment is strongly dependent on the observer. Another visual tool is a so-called tension meter. It is also a visual tool because at least you look with your eyes, you have not really a sensorics here. That instrument consists of an illumination on one side, which projects also again a pattern on the surface, and this pattern is observed here via an ocular in the first versions. Later that was done by a polarized camera, which allowed then also to document the quality of the surface. But finally, the observation and the ranking is done visually. And the pattern here are parallel lines with different distances becoming smaller and smaller. And the name tension comes from, it remembers on a rubber. You see here on a lower quality that the rubber is not with high tension, and the higher the tension is, the more parallel the lines will appear when you look through it. The ranking is from 1 to 20, where 1 is very bad and 20 is very good. So when you see here more and more that the lines touch each other, the quality becomes worse then. And now I come to an instrument which is based on camera technology. So that means it's not just a sensor, a silicon sensor. There is a CCD camera consisting of many sensors, and we have here a defined illumination, a light source on the one hand side, and the camera evaluates then the quality of the reflected image here. And you see here, if you have a perfect surface, let's say a black glass, you see very parallel outlines and a very clear and sharp image. If you have a practical sample, there is some diffuseness, scatters light introduced. That instrument had a measurement range for orange peel approximately from 1 to 6 millimeter structure size or wavelengths. It evaluated 3 values, luster and sharpness for glossiness and distinctness of image, and 1 value for orange peel itself. But mostly used in the market was then the combined value, which is calculated using these 3 values, the so-called CF value. And this has a range from 25 to 95.4. A little bit strange, these numbers, but this is the working range of the instrument here. This is one example. There were some more instruments coming in these 1990s. I will jump now to the wave scan itself and the measurement principle here. The wave scan idea also goes back in the 1990s. 20 years now, a story I have to say, which was growing. You see here on the left side, the first wave scan, which started with a very small display, showing just 2 values for the quality, the long waviness and the short waviness. But a year later, we introduced WaveScan Plus, which had a larger display and also the possibility to let the data flow into a kind of database software that was AutoChart and a trend screen in the beginning. Some years later, we introduced additional filters to have better evaluation of newer paint systems, and we introduced also a camera-based system to evaluate the distinctness of image, the image forming qualities. And shortly later, we had a smaller instrument even available, which allowed then also to measure curved and very small parts like mirror housing, trims, and so on. But I think most of you know in the meantime here the WaveScan Dual and WaveScan 2 family. The WaveScan Dual was developed especially also to have the possibility to measure on primers and medium gloss surfaces, and the WaveScan 2 was specialized on high gloss top coat finish. Coming to the measurement principle now, I want to remember you that our appearance perception is dependent on the distance what we focus on. When we look on the surface, we have the possibility to look on a reflected image via the surface. So we evaluate the so-called image forming qualities. How good can the surface reflect any object from the surrounding? But when we want to evaluate scratches, craters, but also structures, we need to focus on the surface itself, which is a smaller, a shorter observing distance, and then we can get an impression about structures and waves. The waves measurement principle, when we look first on the short distance here, focusing on the surface, is based on a laser system. So we illuminate the surface under 60 degrees with a laser. The light is reflected on the surface, and on the opposite side we have a sensorics consisting of 3 apertures, and these detectors take a scan. So the instrument is moved over a defined length, mostly use 10 centimeters, and over these 10 centimeters thousands of measurements are taken. So you get then what we call an optical profile, the intensity from point to point, and this intensity changes by the angle of the structure, of course. The instrument gives then 2 values, and this is done by a mathematical filtering. We sort then these structures into small structure elements and larger structure elements. This is the short wave finesse and the long wave finesse. And the range for structure size is then between 0.3 to 12 millimeter. Short wave goes from 0.3 to 1.2 millimeter, and long wave from 1.2 to 12 millimeter. Some years later, more and more environmental friendly coatings required changes in the coating principles, and we found then limitations in the correlation there. And therefore, we developed the instrument further and increased, on the one hand side, the resolution here down from 0.3 to 0.1 millimeter, so finer structures that required 2 additional smaller apertures to allow that higher resolution. We then also splitted the long wave finesse into 2 additional filters, and we also added a filter for the longer waves larger than 12 millimeters. So we have now in total an expanded measurement range from 0.2 to 30 millimeter wavelengths. This is again focusing on the surface. If we look on the image forming qualities, we implemented additionally a camera-based measuring system. So we had an additional illumination under 20 degrees, which allowed then to evaluate a contrast reduction. Therefore, with the camera, we evaluate a center area. This is where the main reflection on a perfect black glass plate would be reflected. So this gives a so-called maximum reading. But if we have then a real practical sample, usually we have an amount of light scattered under certain directions. And with the camera, we evaluate this scattered light, and then we divide each values then and get then a kind of relation, not only one measured intensity, it is a relation then, which can express something of contrast, but also the sharpness and distinctness. We call this value dullness. This is a kind of opposite of brilliancy, and the reason is that allows us to implement this value into the so-called structure spectrum for structures which are smaller than 0.1 millimeter. Why 0.1 millimeter? Because this is the resolution of the human eye. Things which are smaller than 0.1 millimeter, we no longer can see as a pattern of bright and dark areas. We just see a reduction in sharpness or in contrast. But with structures which are larger than 0.1 millimeter, this is of course individually and dependent on the age of the observer. But roughly you can say structures which are smaller than 0.1 millimeter, more and more can see as a bright and dark pattern. So in this way, we get now really a kind of spectral curve, which gives now information not only about the quality of the surface, but also about, let's say, causes and reasons for a certain amount of structures. And therefore, I will give you one example here. This is the influence of the film thickness of the top coat, of the clear coat. In this example, it is a two-component clear coat applied in different film builds. You see here from 50 microns down to 16 microns. And you see there a strong difference between these four curves. And you see here the strongest influence here of the thickness is in a range from 1 to 30 millimeter. That means in the range of orange speed, the macroscopic, more macroscopic structures. In that example, you see structures smaller than 1 millimeter, the fine structure, are quite similar. There's no that significant difference between these four samples. And this is a very rough orientation for you. You can say under approximately 0.5, 1 millimeter, these are usually causes coming from material, being the paint, additives, being the roughness of the surface of the primer or of the metal sheet. And if you are in the range of the WC and WD, larger than 1 millimeter, you come more and more to the application process. That can be the film thickness, that can be the distance between the paint equipment and surface, that can be the viscosity, temperature, many influences which can have an impact here. I will give you one example also to give a little bit more feeling about this interpretation of the spectrum. You see here four surfaces with very different spectral curves, and you see here the expression balance. I think some of you have heard that before. One point is really how is the balance between the smaller structures and the larger structures. And here the first example is a very rough thing. You can see here all values in the structure spectrum are very high. And what we could do in a first step is to improve the top coat, let's say reduce the film thickness, for example. And that will lead here to lower amount in the larger structures, and to see as a result that now, in general, it looks more smooth, but the fine structure is more dominating now. We see the fine structure really in the foreground, even compared with this awful example in the first step. So when we want to reduce now this fine structure, as I said, we need to go into the materials more. We could, for example, introduce a sanding process on the primer. And you see here in the third example, this is very strong done. You see these small structures are lower even than the long wave values here. And you see also now, the fine structure is nearly no longer visible, but therefore now again, these larger structures become more visible, very dominating. So this is also not liked by everybody. So the answer could be anywhere in between, and to introduce a little bit short waveness additionally. But then we come into a point where I have to say that can be different from company to company, that can be different on a horizontal and on a vertical. And that's why, besides these very analytical tool of the structure spectrum, different companies use also an amount of 1, 2, 3, or 4 scales just to evaluate the final quality more in the language of quality control numbers, also to be used for pass-fail, for example. And these are often scales which are based on that what people were used to for many, many years. That's why I told that a little bit about the history of the evaluation here. But also we have new scales here. And for example, Volkswagen Audi Group, they used for a long time long wave and short wave. BMW here found that short distance under 1 meter and large distance under 3 meter observation can give a note for an evaluation what they were using. And you see here quite different values up to even Toyota, which had a different sensorics even. I want to point out here especially 3 examples: the Fiat Chrysler scale, the farm value. I come now in the following. And for Hyundai, the PEC value, which will be additionally to the CF value. And then also newer developments of Volkswagen Audi in the following. How are these scales usually developed? Often it is a kind of 2-step evaluation. They have usually so-called reference panels. You see that here in that picture that was, for example, at BMW, where they have many reference panels showing different shades of quality of typical processes there. And these panels are ranked by a representative group of people and ranked in a scaling from good to bad or whatever criterion they were used to. Then these panels are measured also with a wave scan, and then comparing the visual ranking and the instrumental values, it is then possible to calculate scales which are corresponding to that what they are used in their visual evaluation. In the next step, of course, it is needed to verify the results on in the practice, how it works then at least. And this is often done on real car bodies. Yeah, so in the second step, they were used on the instrument were used with this calculated scales on car body, and also a visual evaluation take place, and then compared how good the 2 ways fix together. So sometimes there might be even a correction step or even a second correction step, but at the end you have then a scaling to that what the people are used in the quality control and in the production in the company. And now I will come to a new customer scale. This is was done for Fiat Chrysler, that started in 2012 with a team of Fiat engineers from quality control, materials laboratory, and they used as a starting point so-called ideal curves, ideal harmonic, well-balanced curves without any dominating waviness. And they measured many samples there. They had at the end about 70,000 curves and evaluated then based on that curves with a very good correlation to the visual. And this new scale was called an FAM, Fiat Appearance Matrix, And the ranking there is going from 1 to 12. And I will show you in the next. The main inference there is the level of the WA and WD value, but very important also the balance again between WB and WC, and also WD and WC. So in the such a spectrum, they use also the relation between these 5 or 6 filter ranges here. They found very bad is if you have only one dominating wavelength, like here on the left or here on this example. So if there's no double hump like you see here in the upper part, yeah, that often looks not so good. You see also here, if the relation is strongly dominated by WD, this is also not acceptable. So they have, on the one hand side, the level itself, but also the relation. And then they show that also in a two-dimensional chart where you have on the vertical the farm value, and on the horizontal a value which is called accuracy. And this accuracy is something like minus points. And what happens there, if you have not a very good result on an individual sample, the point moves to the left side, out of the green acceptable range into a yellow or even a red area. And we have here in this kind of chart the possibility also to show a so-called limit curve and a target curve, where the limit curve is based on the limits which were defined in the standard management. So this is based on their specification, their specified limit values. The target curve represents a set of measurements which are to be done on additional parts of a car body, or can be also done on different days over the process. So this will show you a little bit representing what your process is able to reach. Yeah. So, and now you see here also that with this curve you can see in which area you are close to the target and in which area you are, let's say, close to the limit, and that will show you in which range you can optimize the quality. So it gives you both, on the one hand side, good indication for where you are, and also an indication for what you can improve. I come now to the second new scale I want to introduce. This is now from the Hyundai Motor Company, an evaluation which they initiated because they were working with the CF value, what I introduced in the beginning from the QMS instrument. And this CF value, they found very often cannot really show in all cases differences between two samples. And I have here two different paint examples here, but both ones applied on a smooth steel and on a rough substrate. Yeah, the same for the right example here. And you see in both cases the CF value for the blue and for the red, that means for the rough and the smooth, gave the same value. But visually you see really a significant difference. And this limitation Hyundai wanted to overcome, and they made a lot of studies there also, and found then as a cause of that the WB value, and I think in the picture before, I want to make a little step back, you see that here also Yeah, there must be the cause anywhere in this smaller wavelengths. And that's indeed, you see that here, when you look for each of the scales, how strong the influence is on the CF value for dullness, WA, WB, WC, D, and E. And you see the main influence for the CF here is coming from WD and dullness, and WB nearly no influence. Also for WA, there's only a small impact. So they made, again, also a study with many samples and showed them now here in, this is a rough overview about the result then, but that shows it quite good. What they found for their evaluation with their paint expert, they did on a 2-meter ranking and a small distance of 0.5 meter ranking. They didn't have a strong impact of that 0.5 and 2 meter results, and they saw that the standard deviation of all these evaluations were within a ±1 sigma standard deviation. So they found that one additional value could be enough to give better results than before. And they called this then perceived appearance quality. So that takes a little bit more out what the people perceive, what they see. And to see now this, the influence of the certain filter ranges now from WA, WA, and so on this PEC value, and you see a very strong influence now here from the WB, but again in relation cost connected to the WD value. So, and when we come again to this example from before, you see now besides the CF value here the PEC values. You see for the rough steel we have a value of 6, and for the smooth steel a value of 7.6. So this is really a significant difference which allow now to show the differences. Also here on the left example, also a strong difference again. So the third new scale, I will come to this Volkswagen Audi study, which they started in 2012. They had their representatives of the Volkswagen Group observing many samples. They had test panels representing their different process types, from truck to premium car quality, and that was a study based on a pair comparison. So they always compared two different of the samples, and the observer needed to decide whether they accept the difference, yes or no. And so they come at the end to ranking what structures are preferred. And the result of that study is that the observers were able to differentiate different dominating wavelengths, and also the intensity if wavelengths are quite close together. And to do such a study, it is necessary to look on the wavelengths more in detail. That requires a fast Fourier transformation. But before I explain this fast Fourier transformation, I will point out the influence of the observing distance. I think you all know that when you want to read a newspaper, you need to have it in close contact, and if you are far away, you can recognize only large things. And to see here on the left side the visibility function, which is contrast sensitivity function, it's called, of the human eye. And depending on the distance, yeah, you see more larger or smaller structures. And the Volkswagen Audi used a distance of 1.5 meter, 1.5 meter distance, and used then a combined weighting in this Audi study. And coming now to the Fourier transformation, what is that now? I mean, you have seen the structure spectrum, and the FFT is a structure spectrum with a much higher resolution. Yeah, when you, for example, look on the WD value, this WD comes from structures in a range between 3 and 10 millimeter. So this is a large box. If you make this box smaller and smaller, yeah, you come more and more to a continuous curve for a structure spectrum, and then you can see more details than just having 5 boxes with larger filter ranges. And now on this continuous structure spectrum measured by the instrument, we use a weighting function, which is this Audi contrast sensitivity function, to have a weighting of that raw data, which allows then, this is a little bit scientific, I have to say, but that gives a better differentiation when curves are close together and better fitting to the visual observation then. You see in that example, we have now a dominant wavelength of 4.6 and an intensity or amplitude of approximately 25. And you need to take in mind now that we have, that it can be that we have not only one dominating wavelength, we can have also a second one. And then it is important, where is the second one? Often it is more on the long wave side, but sometimes also you can have a dominance stronger on the short wave side. And therefore we differentiate dominant short waviness when it is more than 2.4 millimeter. This is a more empirical value, a result of the study at least. And you see in this example here, we have here the dominating wavelengths at 1.3 millimeter and an intensity here of approximately 14. Yeah. And now I come to the reason of this differentiation. In some cases, both the small dominant wave and the large dominant wave can be in the same intensity range. And then it is sometimes from measurement to measurement that the data jump and you get not a clear, sharp result for your measurements. And to make that a little bit more clearer, what this means visually, on the left example here, on this sample, you have a dominant wavelength of 6.8, only in the large structure size. On the right example, we have overlaid a small structure, which is also quite dominant. Yes, same intensity here, 17 compared to 19, but really smaller at 1.4 millimeter. And so you see there's not only a quantitative difference, it's also a qualitative difference. They look very different now. And that's why in some cases you need really a secondary dominant wavelength. This is the more theoretical part, and I will come now to the instrument introduction of our new instrument. When we look on the different steps from the Wavescan Plus to the Wavescan DOI, microwave scan, even to the robotic systems and the different scales which we continuously develop with our users in the market. We have now this year a new generation, the Wavescan 3, which comes in a new and very fresh ergonomic design, easy to use with one hand, which you can use ideally not only in the laboratory, but also in the production and in the field outside. The new generation comes also in 2 versions. The dual is from high to medium gloss, and the Wavescan 3 is specialized on high gloss top coat coatings. Especially I want to point out a new very large color touch display with a very brilliant, easy to read color display with new display technology, which is a capacitive display. That means for you a very user-friendly haptic touch. You don't need any strong pressure. It reacts directly, even with gloves, and the display will turn automatically when the instrument is turned. You have a very intuitive icon menu operation. And I want to point out some new functions here. The first is a quick check. So here you can just measure without saving and under any preparation before, just measure a few samples. Of course, you can use your organizers. That means your defined sampling procedures coming from your testing planning from the software. You have a direct access here with this icon, and you have an additional mode which we call measure, to measure test series, let's say just samples. And the new thing here is that you can use your standards even with pass-fail, and when you measure them, the display will show you whether the instrument passes or fails. You get here in colored this indication. Of course, you can look into your memory of the instrument and show the saved measurements you have done, and also you can define your instrument configuration from language, switch off time, and so on. And of course, you can select there your scales, scan lengths, statistics for the quick measurement and the measure mode. New now, you have the option for the Wi-Fi connection. This is an optional function. And you can also protect your configuration, your individual configuration, with a password. We modified also the docking station. This is now smaller, slim, fits well on the desk, and also gives you indication well to see whether you're recharging batteries in the instrument or in the docking station are ready for use. Additionally now, besides the Wi-Fi connection, you can use a cable, an additional USB port. You know, in the past, up to now, you needed always also the docking station when you are traveling. This is no longer necessary now. The instrument comes with the software SmartChart, the processing software to manage your quality data, where you can define your standards with scales and limits, where you can define your sampling procedure to have a user guidance on the instrument in the quality control, and you have then a standard desired for every user, always the same measurement procedure. The data are saved in an SQL database, so you can handle very large data sets and do your analysis over large time ranges. We have filter functions here, which allows you very specific analysis according to model status or whatever. Quite new indeed is a drill-in function, which allows you to click on a part of interest, and to get then directly an indication of the results of the last 20 readings, so you see the history of your production over the time. Also in the print layout, you have more possibilities now to create your own individual reports, and last but not least, you can extract so-called mini databases, which makes it easier to share specific data with your suppliers or your colleagues in any other plant. One word to the correlation between the new generation and the existing instruments. You see here the results of a comparison wavescan 3 and wavescan dual, and you see here very, very good correlation being close to 1 for all scales. So you really get the same readings like you are used up to now. I look on the time. I see we need to come to an end now. I will come to a conclusion with the new instrument. Again, you have a good solution for political control and also for troubleshooting to optimize your process. Some might ask for the pricing due to the economical situation we are faced now all today. We didn't change the pricing of the wavescan family, and we even can offer you a trade-in independent of the age of your instrument. So I think that makes it also for you easy to come to the new family. I think I should point out here, especially for our US customers, that we even lowered. That is, of course, due to the changes in the currency rate, which makes it necessary here to be a little bit more flexible for our friends in the States. At the end, I want to come to an outlook. What can you expect in the near future? And there I want to close also the circle with that what I began. Often it's not only the specification which is a measure of quality. Often it's really how good do the parts fit each together. And therefore, we want to introduce what we call in the color measurement a panel match. How strong is the difference between adjacent parts? And we are doing some studies here to make that possible, to see the differences directly between parts which are close together. So I want to ask my colleague, Gabriela, do we have some minutes to answer a few of the questions maybe?
We are a little bit short on time, but nevertheless, we have a few questions. One, I think, was answered during the presentation already. What is the meaning of CF? The C actually stands for combined, so it's a combined scale that combines the information of sharpness, luster, and orange peel in one number. It's based on the structure spectrum data, dullness, WABCD, and as Friedhelm showed you in the presentation, the main influence on the CF value is coming from the dullness value, that means the brilliance of the surface, as well as the WD value. Then another question was, when we say wavelength, what do we mean with this? Wavelength is the measurement that you see here for the different wavelength ranges. The wavescan measures wavelength ranges between 0.1 to 30 millimeters. And when we talk wavelength, we always mean peak to peak of the wavy structure element. And last question was, what is the specification for long wave, short wave in relation to the new Fiat Chrysler scale? This is actually very difficult to answer. First of all, of course, specifications are automotive OEM specific, the limit values, and they can only be shared by the automotive OEMs maker themselves. Usually you have a specification for long wave and short wave for horizontals and a separate one for verticals. Many OEMs have for the short wave a range, that means with an upper and lower limit. This already goes into the direction that you don't want to be on the short wave very low, which would make the surface very brilliant and therefore the long wave would be more apparent to our visual perception. The Fiat Chrysler calculation, as Friedhelm showed you, is also based on the structure spectrum. It's a ratio. The ratio of the curve is of high importance. They like to have this double hump. And this FUM value is dependent usually by the automotive, segment. You know, for premium, you have a different specification than you have, for example, for standard or for commercial vehicles. So also here it's a combined value taking different conditions into consideration. So we cannot officially just give out the limit numbers. I think the main difference between the Fiat Chrysler and long wave and short wave is that the Fiat Chrysler scale is based on the ratio of the structure spectrum, while long wave and short wave are one-dimensional scales and often are not seen together, but seen as an absolute limit. And then one more question I think we can take. There was the pricing of the Wavescan 3 Dual. So I'm happy to see that also in this difficult time, we do have some interest in maybe purchasing. So the Wavescan 3 Dual is $34,500 US, and it's actually, we really reduced the prices for the new models in the US, or in Americas, I should say. So the new model is lower in price than the existing Wavescan 2 or Wavescan 2 Dual. Okay.
On that point, I want to make a little comment because that question came yesterday. Just to make it clear, it includes the software.
Yes, we always sell a complete system. It includes the smart shirt software. And I think what's also very important, we highly believe in this. It also includes a one-day training. So we want to make sure that everybody knows not only how to use the instrument, but also understand the measurement theory, as well as how to optimize the data, work with the data, and work with the software in regards to data analysis with trend charts. Maybe one more, very last one. It says here, I have orange peel that more resembles a golf ball, and I do not see an ATC card match to represent my visual issue. Should I use N1, N3 to note these issues? I think if you have a really, really rough surface, I would definitely go with the structure spectrum information to see in what ranges your waviness is. And then based on this, please contact us and we can recommend maybe one of the other customer-specific scales for your specific application. Is there a low-gloss unit for Wavescan 3? At this moment, the Wavescan 3 Dual is for high and medium gloss surfaces, but this is maybe a good way to end this webinar also. You should all know we are working on a development project to also measure really low gloss surfaces, which are of course of high interest, especially for compact processes where the influence of the substrate is getting more and more important. And I have to say, it looks promising what we are working on. Okay, this I think brings us to the end. I want to thank everybody who took their time to listen to us, and I would like to hand it back to my colleague, Friedhelm.
Thank you very much, Gabriela. At the end, I just want to point out my colleagues, which we are a group here which can help you further with any kind of question, not only orange peel, waviness, appearance, also color, of course, application questions. On both sides here of the Atlantic and also the Far East, of course, but these are contact people which are happy when you have contact them. You find all these data. I don't introduce each now in single, but you will find these information in the PDF, which we will send you in the next days, the PDF of the demonstration here. And also additionally, you will get then the link of the presentation. I also want to make you aware of our next event. This is in June 17th and 13th, about color control and new also the prediction of color stability that covers, roughly spoken, how to measure color, gloss, what is the influence and how can it be measured, or fluorescence, sorry, and also the prediction of color fading with the help of new indices and with the help of the spectral to guide our new color meter. Also, I want to make you aware of our new website. We are very busy on improving our website here. Big instruments. Take a look there. You will find a lot of very helpful information. You will find very good videos explaining theory, how to use, application hints, and so on. You find the videos also on our YouTube channel. Also there, I want to ask you, please, invite you, please take a look on that. Yeah. Finally, I want also from my side, thank you for your time. We also want to invite you to visit us. Of course, when the lights are green again, I'm sure we will have better times again. And please visit us at our plant, take a look to our production. And again, in Munich, close to the hills and close to a nice beer. Thank you very much and see you next time.